Hello and welcome back to the second lecture of week 5. In the last lecture, we started discussion on the transformer architecture and we said what is the intuition for using attention as a replacement to the previous models like recurrence networks. So we just started on that. So in this lecture, what we will do, we will put more details on self-attention, especially looking into the equations that we need to model self-attention. We will progress from there to the concept of multi-head attention that is used in transformers. We will talk about feed-forward network and then we will describe what is a complete transformer block. Especially till now we are only focusing on encoder, we will see it from the encoder perspective. What is a complete transformer block? Okay, so a recap of what we talked about in the last lecture. So we mentioned about self-attention that can be done in parallel. So if your input is these 4 words, you can compute the self-attention output for each word. So like for the word beetle, the query of the word beetle will attend to all the keys for all the words. It will compute some attention weights and using the weights it will take a weighted average of all the values. And this will be the self-attention output for the word beetle. Now this can be done in parallel to all the words. So you can do it for all the 4 words in parallel. So this is what we talked about in the last lecture. Now like this famous Google researcher has mentioned this to be one of the most important formula in deep learning after 2018. So the self-attention formula. So in equations, how does that look like? So you have the initial word vectors or whatever is the input to the transformer encoder. So this is your input to the encoder. So xi and xj are 2 different input, or you mean to say 2 different words in the sequence, okay, xi and xj. So now how do you compute the self-attention score? So first of all, so this is what you want to compute. Ai for the xi input, what is the self-attention output? This is what I want to compute. And how will I compute it? It's a weighted average of all the values, right? So in the sequence all j's, I'll take a weight alpha ij times vj. So ij denotes from the word I weight for the attention over the word j, right? The attention that ith word is putting over jth word in the sequence. Now how do I compute alpha ij? For that, so for the ith word and jth word, what I will do, I'll get the query from ith word, I'll get the key from jth word, and I take a dot product qi dot kj. But in actual equation, I divide it by another scaling constant called square root of dk. What is dk? Dk is the dimension of key of ki, kj. All will have the same dimension. What is the dimension for the key? Okay, so this vector. So I divide it by a square root of that. This becomes the scale dot product. And we will discuss the intuition for this later on in today's lecture itself, that why do we need this scaling constant. But let's right now go ahead with that. So this is the how we compute the score for each word given ith word, and then once I have computed all the scores for all the word jth word, I do a softmax. Okay, and this gives me alpha ij. So this will give me a score for all the words in the sequence, including the ith word itself. So from the first word to nth word includes ith word and jth word also. I get a score for each word. It's like a probability distribution, and then I take a weighted average of their corresponding values. So this is another visualization to see how this works. So here we have 3 input words, x1, x2 and x3. Think about their embeddings as the input. What I want to do, I want to compute attention output for the third word. I want to compute A3. So what are the steps? So first of all, I need all the key query and value for each word. So I need these 3 matrices, WK, WQ, WV. and this is the same copy I am using. So, using these matrices I project them to a key, query and value for all the 3 words. So, you can call it K1, Q1, V1, K2, Q2, V2 and so on. Now, for computing the self-addition output for the third word, I need to use key from here. So, you see key is taken from here, okay, and I need to take the query from here. Query from here is the main thing, the query from the third word. So, I will take Q3 and I multiply Q3 with the keys for all the words. So, multiply Q3 with K3 for this word, multiply Q3 with K2 for this word and Q3 with K1. Correspondingly, I will get 3 different values. I divide it by square root of dk and then I get 3 scores, alpha 31, alpha 32, alpha 33. Why 31? Because you are taking for the corresponding to third word, what is the attention I have to put on the first word. So, I get these alpha ij's, and so this is after doing softmax. So, you are doing divide by square root of dk, you are doing softmax, you get these weights. Now, you take the weighted average of the values. So, alpha 31 times V1, okay, alpha 32 times V2, alpha 33 times V3, and you add them up, you get the self-addition output. Okay. That is how this works. For individual word, you can do the same for other words as well. You can also try this problem. Okay. It is a toy problem. So, suppose you have 2 words in your input, flying and arrows, and what is given to you, the embeddings of these words are 6 dimensional. So, 6 dimensional embedding for both the words, there are 2 words in the sequence, and you are trying to represent the first word flying. That means you want to get the self-addition output for the word flying, right. So, what is A1, right. So, how do you do that? You need to know what are the projection matrices so that I can get the query, key and value for each. So, in this toy problem, it is simplified for you. So, it is mentioned that for the first attention head, the query, key and value matrices just take the 2 dimensions from the input each. So, that means what you do, you have this input 0, 1, 1, 1, 1, 0. You take the first 2 dimension as the query. So, query is just 2 dimensional 0, 1, next dimension as key and next dimension as value. I mean you may have the corresponding projection matrix. You can find out what is the corresponding WQ, WK and WB that will give you this. But let us say for this toy problem, that is how you get query, key and value. So, you can get it for both the words. Now and you are using self-addition scale dot product. So, what is the self-addition output for the first word? How would you get it? It is not very difficult now. So, I have to get the query, key and value for both the words first of all. Okay. So, let us say we have done this 2 dimension each, Q2, K2, V2. I need to find out A1. How would you do that? For attention output for the first word, I need to take query from first word, multiply it with key of word 1, word 2. Okay. So, Q1 dot K1 in this case is 1 and Q1 dot K2 0 1 times 0 minus 1 is minus 1, right. So, this is the 2 dot products. Now, I have to take a softmax over that. I have to also divide by the dimension of query, right. That is what I forgot. So, divide by square root of dk. What is dk? Dk in this case the dimension of key, that is 2. So, 1 by square root of 2 minus 1 by square root of 2. Okay. So, you have got 2 values. Now, you take a softmax of this. So, roughly softmax of 1.4 and minus, sorry, this will be 0.7 minus 0.7, right. Compute the softmax for this. Suppose you get 2 values. So, you call them alpha 1 1, alpha 1 2. Okay. So, they will add up to 1, they are all greater than equal to 0. In this case, both are greater than 0. So, what is your final output? You now take a weighted average of the values based on that. So, you will take alpha 1 1 times 1, the 1 0 plus alpha 1 2 times minus 1 1. So, in terms of alpha 1 1, alpha 1 2, your final score will be alpha 1 1 minus alpha 1 2, the first dimension, and only alpha 1 2, the second dimension. So, once you compute the self-addition output, you can get this final. Once you compute this softmax, you can get the final self-addition output. Okay. Okay. So now we talked about self-attention, where we think, okay, given a word, I can get 3 projection matrices, and I can use query key and value and use that to get a self-attention output. But in the paper, the transformer paper, they introduced multi-head attention. That is, okay, why are you doing it only once? Who is preventing you from using multiple matrices? So I have multiple copies of this. So I can have WQ1, WK1, WV1 for the attention head 1. For the head 2, I can have WQ2, WK2, WV2, right? Another copy which can have completely different parameters. So you're learning to project in various different ways, and you are getting different kind of output. So you can get self-attention output from the first head, from the second head, third head, and fourth head, and combine them to get your final output. Right? So this was the multi-head attention concept. Starting from single head, you have multi-head attention. So why do we need this multi-head attention? Like intuitively, what would happen in an attention, I can give a distribution that given a word I, which words it has to focus on, and in the distribution only some words may be preferred, right? But what if you may have multiple ways of attending? Maybe you want to attend to neighboring words separately, you want to attend to rare words separately, you want to attend to the pronouns separately, right? So how can you do that in a single attention equation? So the idea was, why don't you use multiple attention heads and let the model learn which attention head will focus for neighboring words, rare words, or whatever phenomena that is relevant for your task. So that's what is the idea. We will define multiple attention heads through multiple QKV matrices, and each attention head will perform independently. So we will not combine them. I mean, we will not connect their weights. We will not have the sharing of the weights. So we will be learning independently, and once we get the output from each head, we can combine them. So it was done through concatenation. So each head will get to look at different things, and it will construct the value vectors, the weighted value vectors, differently. Okay, so this was actually one of the papers in 2019 that tried to analyze multi-head self-attention. So what they found that there are at least 3 important types of heads. Right? What they looked at various attention matrices, and they found at least 3 types of heads. One is the positional heads that attend mostly to their neighbors. Then there are syntactic heads, because in a sentence we talked about syntactic recency versus sequential recency. So given a word, syntactically it may connect to a very far apart word. It may not be a neighboring word as per the sequence. So you may have some syntactic heads that will point to token with a specific dependency relation, a specific syntactic relation. And then there are heads that point to rare words in the sequence that may be very, very important for attending to that word. Okay. So at least these 3 types of heads, but you may have other kind of phenomena that are captured by multi-head attention. So in terms of equation, how does that look like? So it's very similar, except that now you have multiple matrices, multiple query key and value matrices. So each head might be attended to the context for different purposes, which may be different linguistic relationships or patterns. So what will happen? So from QXI, that was the original word embedding or the input to the encoder, I can have WQC for the cth head, and I will correspondingly find the query for the cth head, key for the cth head, and value for the cth head for the same word. Okay. So and then you can compute this code exactly in the same formula, but you will say, okay, now this is for this particular head, another head, and so on, and I'll have attention weights per head separately. So for head 1, I'll have one matrix alpha ij for head 1. For head 2, I'll have separate matrix alpha ij2. So I have 2 different matrices, and then my output will be, so I take a weighted average of these. This will be my output from the first head, self-attention output from the first head. You just concatenate. This is the concatenation operation. You concatenate these h heads together, and then you multiply with the matrix W out, so that you have an all pair interaction between the heads, and you get the final output. So this is how we use the multi-head attention. So you are, rather than doing this operation once, you are doing it multiple times using multiple matrices, and then applying it with some another projection matrix to get the final attention output. Okay, because what should happen, this attention output should be actually the same as your model dimension. Okay, so this is one visualization. So what is happening for the ith word? You are attending to all the words in the sequence. So you have multiple heads, head 1, head 2, up to say head 8. In the transformer paper originally they introduced H heads, 8 heads. Okay, so let's say there are 8 heads. So there are 8 matrices. Now, what is the output for each from each head? So the output is actually the weighted average of the values. So that means the output dimension of each head will be the dimension of the value, right? Because you take a weighted average of the value. So each head is the dimension 1 cross dV, right? Each head is 1 cross dV dimension. And now finally you concatenate all these, combine all the outputs. So this will be H times dV, okay, H times dV. And then you want to project it back to the D dimension, the model dimension. So that's why this WO matrix is H dV times D. That is your WO matrix. So this will project it back to the D dimension, the model dimension, and that is what is called your self-addition output for the ith word. And you can still do this in parallel using all these 8 heads that you have. Okay. So another visualization from the book. So you have a sequence x1 to xn, and you have multiple heads. In this case, 4 heads are shown. You used different matrices for each head, and you get output from each head. You concatenate this and then multiply with matrix WO that will project it back to the D dimension. That was the dimension of the original input for each word. Okay, and this would be the output for the nth word. Let's say this is for the nth word. This is the self-addition output for the nth word. Okay. Now, if you try to look at the dimensions, right, this will also give you an idea how many parameters are required. So you see, what are you doing? So in the original paper, the input dimension, model dimensionality is 512. Okay, and they took the query key and value dimensions as 64 each. So dk is equal to dq is equal to dv is equal to 64. So that means each of these matrices wqi would be of 64 cross 512. Right. All of these are 64 cross 512 dimension, and you have 3 such matrices, right? Times each matrix for one head. So we will work out the parameters in the next lecture, but you can see how we will do this. So we have each matrix of this dimension, and you have 3 such matrices, and you have H such heads, so 8 such heads. So you multiply this with 8 times 3, right? Then you have WO matrix, that is, you project HDV to D. So another HDV times D matrix W. So these are the parameters that you need just for self-attention, multi-head self-attention, right? And we will try to work out these parameters in detail in the next lecture, but you can try on your own once. Okay, fine. So what next is there in the transformer block? So we talked about self-attention as like one of the most important ideas, right? What else is there? So till now, what is happening in self-attention? You are simply taking a weighted average of all the values, right? So there is no non-linearity that is being introduced here. So this is simply performing a re-averaging of the value vectors, nothing else. So how about introducing some non-linearities? And that is why we have a feed-forward network. So what will happen? So each input xi will get a self-attention output ai, okay, by taking averaging of values for all the words in the sequence. Now on this output you will apply a feed-forward network, and this will be the feed-forward output, whatever you want to call it, fi. Right. You get an output of from the feed-forward layer. So this will again happen for each word. So from xj again you will get the aj self-attention output for the word xj, and you apply the same feed-forward network. You get fj. Right. So you get another output, and you will maintain the dimensionality. This will also be the same model dimension that was the input and also the self-attention. All word will be d-dimensional model dimension. Okay. So that's what we do. So on the self-attention output, we apply a non-linear activation and some additional expressive power, right, through this feed-forward layer. So what exactly happens there? So think about this as a self-attention output. Output for Beetle, drove, and this is what you call as the input, You apply a matrix W1 to take it to some hidden layer. So xi W1 plus some bias parameter. You introduce a nonlinearity there in the hidden layer. Then you go from hidden to output so that you maintain back the dimensions. So you apply another matrix W2, okay, and a bias parameter B2, right. So this is what is a very simple multi-layer perceptron where you have one hidden layer, right. So how many more parameters you are introducing here? So you have W1 matrix and W2, of course, with some bias parameters. So in the original paper, what they did, they had this 512 dimension output. So they introduced 2048 dimension, the hidden layer. Okay, so this was 4 times t. Typically, that was the rule that later papers also followed. So if the model dimensionality is t, so your hidden layer is 4D. So your W1 has 4D cross D parameters, and W2 again has 4D cross D parameters, because you project 4D back to D. Right? I mean, if you really want to do it correctly, it will be D cross 4D. Okay, and this will be 4D cross D. Right? So this will ensure that finally you will get back to your D dimension. Right? I think this in this equation this should also be D cross 4D. Yeah. So let me check again. So you have this part is of dimensionality 4D. So you want to multiply it with W2. So yeah, it should be 4D cross D. Yeah. So you have 2 different matrices that are introduced in the feed forward layer. Okay. So yeah, these are the 2 important blocks that you have in an encoder, and then you have a stack of encoders. So in the original paper there were 6 such encoders, right. Now that's where the problem starts. So you are saying I will do the self attention and feed forward layer once, not once, I'll keep on repeating it again and again. So I will do the same thing in the next encoder, and so on. And recently you will see there were in the recent papers there will be hundreds of such blocks of transformer. So what are the tricks that you need to make sure that this actually works and trains well, right? So there are various tricks that were used to ensure that this actually works. So we'll talk about some of these tricks. So one is residual connection or skip connections. Skip connection. Second is layer normalization. Third is the scale dot product attention that we left out earlier. So we will talk about these as the tricks for training these models well. Okay. So what is the residual connection? So idea for this came from the computer vision domain. So you might have heard about the paper ResNet, so which introduced this connection, this skip connection. So what is the idea? So let's see in the context of transformer. So you're giving this embedding xi and producing some query key and value from this, and then you're using some self attention, right? But then what will happen? Finally, you have the average, I mean weighted average of the values. But what about the original input, right? So you might forget what was the original information. So how do you ensure that you do not forget the original information? So what you do, you say, okay, why don't I add it back? It's a very simple idea. So you get the output AI and you add the input again, right, to this. So you retain the original information. So AI plus xi. Fine. Next you apply feed forward and again add whatever was this. So AI plus xi was applied to feed forward, FFN, plus you add AI plus xi to this. So you retain this information. Okay. So it's a very, very powerful technique. So because what is seen is that these deep networks become very bad at learning some sort of identity function or preserving the original information. So this is one way in which you explicitly give back the original information. So therefore what will happen? So directly passing the raw embeddings to the next layer. So you have xi minus L minus 1 as the embedding, plus the output of the function can be self attention or feed forward. You add this raw input again, and that becomes your actual output. Okay. So that is the whole idea. So you have this add block. So you add the original input and you keep on doing that again and again, right? So this is one important trick, residual connection or skip connection. Second trick is layer normalization. Now you will say, okay, I'm adding these things, but what will happen to the mean and variance, right, of the features? So you have the original embedding xi, and then you are keeping on adding more and more things on that. You're adding, so AI plus you're adding xi, right? So its mean and variance will change. So it will keep on changing, right? So you have multiple layers. You don't just have one layer. You have multiple such layers. So what will happen? It will keep on increasing. So the layer normalization trick is that you keep bringing back to the same mean and variance. So typically you want to bring it back to mean 0 and variance 1. Okay. So input from the layers keep shifting because of this addition, right, to this connection. Solution is that you reduce this variation by normalizing to 0 mean and standard deviation of 1 within each layer. So how would you do that? So let's say you have AI as the output. Okay, so AI, AI1, AI2, and so on is the output. You take a mean and standard deviation and then put it back by standard formula to divide minus the mean divided by standard deviation plus some epsilon term to ensure whenever all values are same, you don't just divide by 0, right? If the standard deviation is 0, you don't divide by 0, just ensure that this is non-zero, right? So ensures that this is a small epsilon is a very small positive parameter that ensures that you have you don't have the divide by 0 problem here. Okay, so you simply take the mean and standard deviation of the different features and put it back to 0 mean. So by subtracting mean and dividing by standard deviation, you ensure that this becomes 0 mean and 1 standard deviation. Okay, so just to give you an example. So let's say we have multiple samples and we have 4 features. So think about 4 embeddings. So they have 1, 3, 5, 7 as the value, 3, 4, 6, 2 as the value across different samples. So what you will do, you will take an average. Mean is 4, standard deviation is 2.23. So what you will do, so 1 will go to 1 minus 4 divided by 2.23 plus whatever is the epsilon, right? And similarly 3 will go to 3 minus 4 divided by 2.23 plus epsilon. So you normalize these values across features. So you do it across this dimension. So for each sample, the features are normalized to 0 mean and standard deviation 1. Of course, if you will see the original transform paper, they introduced 2 more parameters here. So they said, okay, so rather than going to 0 mean and 1 standard deviation, you can go to some gamma mean and beta standard deviation. And this you can do simply by multiplying this whole thing by beta plus adding a shift gamma, right? Beta XL prime plus gamma. This will take it to mean gamma and beta standard deviation. But later papers also found this gamma and beta is not so helpful. So they typically work with just mean 0 and standard deviation 1. Okay. And the third trick is the scale dot product. So that is when you are doing this qi dot kj, you are dividing it by square root of dk, dimension of k. Now why are we doing that? So remember this idea about going back to mean 0 standard deviation 1. So this will also be the output. So ai, this will become the alpha ij, right? So we want it to again be going to mean 0 standard deviation 1. So what happens after layer normalization? All your values are mean 0 and standard deviation 1. But when you do dot product, what changes, right? What changes? So let's see. So what happens if I do dot product of qi and kj? So you can just use a bit of statistics. So what you will find when you do this, the mean will become 0, but the standard deviation becomes dk. And if you divide it by square root of dk, the standard deviation will become 1. That is the region. But how do you come to that? How do you get this variance as dk? So let's do that quickly. So let's say we have two q and k that you are multiplying, right? So they are vectors. So there are, let's say, dk different vectors. So you have q1 to q dk and k1 to k dk, right? It's the vector, the query vector and the key vector, right? It's not multiple queries and multiple keys. It's the same query and same key because this is a vector, right? Dk dimension vector. Now when you do a dot product, what will happen to the mean? So what is the mean of q dot k? So it's expectation of summation I is equal to 1 to dk qi ki, right? Now expectation can go inside, so you will simply say it's equal to summation I is equal to 1 to dk expectation of qi times expectation of ki, and this is easy because each of this is mean 0. So, there you only multiply with 0. So, this you get 0, mean is 0. Okay, this is easy. But the variance, how do I compute variance? So, what will be the variance of q dot k? This will be expectation of q dot k square minus expectation of q dot k square, right. Now, this we have already computed, expectation of q dot k is 0. So, this is 0. So, we just have to worry about this term. What is that? This is expectation of, so now you will have a square of term. So, you will have qi square, ki square for all I, right, dk times, plus 2 times some qi qj, ki kj for all possible ij pairs, right. That is what you will have. Now, think about the first term, because each term has variance 1. So, expectation of qi square times expectation of ki square is nothing but the variance, individual variance 1 dot 1 is equal to 1. So, this will contribute to dk here, while here you will go back inside expectation of qi times expectation of qk, everything is 0. So, this will contribute to only 0. So, the variance becomes dk, right. But if you divide it by square root of dk, this will become just 1, right, because if you divided them by square root of dk, because square term you will divide by dk, and this will become 1 finally. That is why you divide it by square root of dk. Okay. So, now we talked about the 3 tricks, and we are ready to talk about the complete transformer block, okay, at least the encoder part. So, let us see what we will do. So, we have the input, the Beatle drove off, and let us say we get the embeddings x1, x2, x3, x4. First, I apply multi-head self attention to get the self attention output A1, A2, A3, A4. We talked about that in great details. Next, what we will do? We will add it back as a skip connection. Okay. So, we have a skip connection, we add it back, okay. And because we have added it back, we will do a layer normalization to ensure that the values are mean 0 and variance 1. All right. So, this complete thing is sometimes called add and norm, add and normalize block, and this you will do repeatedly. Okay. So, again next what you will do, you will apply a feed forward network on this output, a feed forward layer. So, you get the corresponding outputs after applying to W1 and W2, going back to model dimensionality. So, all of these have the same dimensionality D. Next what you will do, this is the feed forward layer output, I will put it back as the skip connection. Okay. So, I will add it back, and because I am adding it back, I will do layer normalization, and this becomes the output for my one transformer encoder, and this will be fed to the next encoder layer as the input. This will become input to the next encoder layer. Okay. So, we still have not talked about one more important thing that is still lacking in this encoder. You can think about it. So, for example, if I would have changed the word order to the Beetle drove the off, or Beetle off drove the, nothing will change in the individual computations, right. Computation will not change if I change the word order. So, how do I incorporate that information, right? Because the good thing about transformer is that you do not have sequential dependency, but how do I preserve that information? Right? So, we will see that in the next lecture. Okay. So, yeah, this is another way of visualizing the same block. So, you have input sequence, you apply self attention layer, you add it back as residual connection, do layer normalization, this is the output, you do feed forward network on this output, add it back and do layer normalization, you get the final output for each word. And you can get such representation, the contextual representations for each word from one encoder block. Okay. So, chapter 9 of our book talks about this in more detail. You can go through that, and we will continue from here in the next lecture. Thank you.